Hello everyone, this is Dr. Webb, and in this abstract algebra video we are going to be starting a whole new topic, a whole new broad range of ideas, and this all falls into what is called rings or ring theory. So this video is going to be presenting the basics about rings and then talking about one important subcategory of rings, which is called integral domains. One bit of warning at the beginning, because this is a new area, there's an awful lot of definitions that are going to be coming in. So this is going to be very definition heavy. There are going to be some basic theorems in here, but the proofs are really not very involved. But a lot of this is going to be, there's going to be a lot of new terminology to digest. On the other hand, one thing I will say, though, is that rings are something that you have seen an awful lot in your life. In fact, pretty much any time that you have done arithmetic before, you have been doing arithmetic in a ring of some sort. And so I think that's important to keep that in mind, that really this new terminology that we're using, we're just giving terminology to structures that actually you are pretty familiar with. So let's jump into it. What is a ring? And so what makes a ring different than a group is that whereas a group had one operation, a ring is going to have two operations. And we're going to call those two operations addition and multiplication. Now, both of these operations are closed and associative on the set. Addition is always going to be commutative, and so this is similar to how we thought about addition in groups. So addition is always commutative. Furthermore, addition there's going to have an identity, which we are going to call 0, and so this is the additive identity. And so a plus 0 is equal to a, and since it's commutative, this also means that 0 plus a is equal to a. Also, in R, everything has an additive inverse. And so for any a, there is a minus a, such that minus a is in R, and not only a plus minus a being in R, really this should say a plus minus a equals 0. This is the important idea with the additive inverse. And so for addition, putting these categories together, this means that a ring with addition is a group. So ring over addition, so with addition, is a commutative group, so is an abelian group. And so as we've seen, abelian groups, those are pretty much the nicest groups you can have. So when we have a ring, when we talk about it with addition, it is a full abelian group with addition. Now for multiplication, the only stipulations we have on multiplication is that it's closed and associative. So it doesn't necessarily have to have an identity, and it doesn't necessarily have to have multiplicative inverses. But what it does have to have is the distributive property. And this is the same distributive property that you saw in grade school, where if you do a times the sum b plus c, you can break that up as ab plus ac, and b plus c times a is equal to ba plus ca. So notice we had to write it two different ways because we don't know, we're not saying that multiplication has to be commutative. So addition, full abelian group. Commutative, closed, associative, additive identities, additive inverses. For multiplication, all we're saying is that it has to be closed and associative, and then it has to have this distributive property that allows it to play well with addition. So, examples of rings. So pretty much the structures that you've done arithmetic on are all examples of rings. So the integers, the rational numbers, the real numbers, the complex numbers. Z mod NZ. We can do both addition and multiplication when we're working mod n. So Z mod NZ, this is an example of a ring. You have 0 in there. Depending on n, things always have additive inverses, but they may not have multiplicative inverses. But the basic rules of arithmetic, including distributive property, that always holds. Matrices. So matrices, so we're going to let M sub nr be a set of n by n matrices where the entries are coming from some ring R. And R could be any of the rings above. It could be any ring, period. And you can talk about matrices on that ring. That is always going to be a example of a ring. And so for the matrices, again, this is the same arithmetic you've done on matrices before. Addition is done entry by entry. And then we have, since we're doing this with square matrices, this is normal matrix multiplication, is the multiplication operation. Given a ring, you can look at the set of polynomials in some variable x. And so this is the polynomials where the coefficients all come from this ring. This will end up being a ring. You can also look at the formal power series. So we're looking at formal power series, so we're not concerned about convergence. We're just looking at power series in some variable x where all the coefficients come from a ring. This will be an example of a ring. And the list goes on and on and on. Okay, so here's some more terminology. In a lot of these rings that we were just talking about, they also have a multiplicative identity. And so multiplicative identity, which we will call 1. So this is a element of the ring such that for any other element of the ring A, we have that 1 times A is equal to A and A times 1 is equal to A. If a ring has a multiplicative identity, then we will call it a ring with unity. And so unity meaning has a multiplicative identity. Okay, and so I think we use unity because there's really in a ring, if it has a multiplicative identity, it also has an additive identity. And so this is to kind of break that up. You know, instead of just saying ring with identity, we want to certify that we're talking about a multiplicative identity. If for some element in the ring, it has a multiplicative inverse, because remember, in a ring, elements don't have to have multiplicative inverses. But if it does have a multiplicative inverse, and this is an inverse in the normal sense that A times A inverse is equal to 1, the multiplicative identity, then we're going to call that element A that has an inverse, we're going to call that a unit. Okay, so an A with inverse is a unit. Now the multiplicative identity, it is always its own inverse, because 1 times 1 is going to equal 1. So if it has a multiplicative identity, that is always going to be a unit. If the multiplication operation in R is commutative, then we say that R is a commutative ring. Right? So remember, in these two operations, addition is always commutative. And so multiplication being commutative, that's a bonus. Right? And so when we're doing things in the integers, or the rational numbers, or the real numbers, or the complex numbers, or z mod nz, or with polynomials, those are all examples of commutative rings. Polynomials, if R is a commutative ring, then the polynomials with coefficients in R, that is going to be a commutative ring. Matrices, on the other hand, we're very familiar with matrix multiplication not being commutative. And so matrices, that's an example of non-commutative rings. So the 2 by 2 matrices over R is a non-commutative ring, and that's because addition is still commutative, but multiplication is not commutative. Lastly, if we are in a commutative ring, and we have two elements of AB in the ring, and there exists some element K in the ring, such that A times K equals B, then we will say that A divides B in the ring. And so we will write that as A divides B. Now this is something that we're very familiar with in integers. This is terminology we've been using for integers quite a bit, where if you have two integers and you can write one as a multiple of the other, then it divides the other. Now in some rings, this is a fairly silly thing to say. For example, if you are say in the rational numbers, pretty much every non-zero rational number divides every single other one because you can find some fraction that turns one to the other. And so really for this divides part, we're really going to focus this on the places where it doesn't happen all over the place. So in rings like the integers, say. Now let's talk about some basic properties of rings. So first of all, anything times the additive identity is going to give you back the additive identity. So anything times 0 is going to give you 0. And here's a quick proof of that. If you do a times 0 plus a times 0, well, by the distributive property, I can factor out the a, and this is going to be 0 times 0, but then 0 plus 0, but then 0 plus 0 is just 0. So this is the same as a times 0. And so then we can, since addition is a full group, I can do cancellation of the a zeros, and you end up with a0 equals 0. A times 0 equals 0 for any a. Now, if we have a times minus b, this is the same thing as minus ab. And so really you can kind of factor out these minus signs. And so I'll do a quick proof of the first one. And so the idea is that if you have a times b minus b, well, this is going to equal a times b plus a times minus b. And on the other hand, a times b minus b, this is equal to a times 0, which before we saw is 0. And so now we can add minus ab to both sides. It cancels off the plus ab on the right-hand side, and we get minus ab is equal to a times minus b. And we can do similar proof to prove the second one. And so I'm going to skip that. Similarly, if we do this again, sort of apply this twice. If you have the additive inverse of a times the additive inverse of b, that's the same thing as ab. So two additive inverses multiplied themselves out. The minus signs cancel. This is what you're familiar with. The distributive law also works if you swap out addition for subtraction. And so this is really just the same as thinking about b times minus c. This is the same as b plus a times minus c, and then using the second property up there, this is ab minus ac. And doing multiplication on the other side doesn't change anything. Okay, now what if we have rings with unity? Well, so if it has a multiplicative inverse, then this multiplicative inverse has a negative. And so we have minus 1 times a is going to equal minus 1 times a by what we saw before. So this is equal to minus 1 times a, but then 1 times a is just a, so we have minus a. Same as before, if you have minus 1 times minus 1, so we're just applying this directly to doing minus 1 times itself, this is going to mean that minus 1 times minus 1 is 1. So minus 1, if 1 is the multiplicative inverse, then minus 1 is going to be its own multiplicative inverse. So some other things that are true that we have proved early on. We proved this really in terms of groups. And so I'm not going to rewrite the proof right here, but one is that if a ring has a multiplicative identity, so if it is a ring with unity, then that multiplicative identity is unique. There can only be one multiplicative identity. Similarly, and this is because multiplication is associative, If a element in R is a unit, if it has a multiplicative inverse, then that multiplicative inverse is unique. It can only have one multiplicative inverse. And again, this follows from the fact that it has that multiplication is associative. So if you have a ring, and then you have a subset of the ring that is also a ring, then that subset is called a subring. Okay, and so if we have a subset S of a ring R, it's also a subring, and it is a ring itself, then we call it a subring. And so this is using the same operations as R. And so we have a subring test. And so for a non-empty set S of a subring of a ring R, then it is a subring if it is closed under subtraction or multiplication. In other words, for any A, B, and S, we have A minus B is in S, and A times B is in S. Okay, I'm not going to write a full proof of this, because really this is just pulling together really this is just pulling together things that we've already seen, right? And so to prove that S is a subring, we need addition to be a group, and we already know that it is that it is associative and that it's non-empty. And so to finish proving that it's a group under addition, we can then use the one-step subgroup test and checking if A minus B is in S. This is the one-step subgroup test for addition. And so since A plus the additive inverse of B is an S, it passes the one-step subgroup test for addition, and that means that it is a subgroup under addition. And then lastly, the only thing left to prove is that multiplication is closed, and that's there. And if these are true by the distributive property that we have for the ring, this is inherited into the subring, and so there's nothing left to prove there. Okay, and so for a subring, to prove something is a subring, all you need to do is show that for any two elements, one minus the other is still in the subring, and that the product of any two things in the set is inside the set, and that gives you a subring. Okay, I'm going to give you a warning right now. We are about halfway through the material for this, and so if you want to take a break, pause this right now, go get yourself some coffee or some water, take a couple deep breaths, meditate, do some yoga. Now is a good time to do that. So I'm going to pause for a couple seconds. If you want to pause this video right now, go off, come back to it in a little bit. This is a good spot to do that at. Okay, so now we've talked about basics of rings. Now we're going to talk about some important subtypes of rings. And so the first important notion that can happen in a ring is we have something that's called a zero divisor. And so what a zero divisor is a non-zero element, A, of a commutative ring, such that there exists some other non-zero element, B, in the ring where you have A times B equals 0. Now, this doesn't happen in a lot of rings that we're familiar with. So this doesn't happen with the integers or the rational numbers or the real numbers, but it can happen in other structures. So let's say, for example, in Z mod 6Z. Well, what if you do 2, that's a non-zero element, times 3, 3 is a non-zero element, but 2 times 3, that's equal to 6, which is congruent to 0 mod 6. And so this means that 2 and 3 are zero divisors. In Z mod 6Z. And so the name zero divisor literally means I have found something. For 2, I have found some other element of the ring, 3, to multiply it in to give me 0. And so literally, we have shown that in this ring, 2 divides 0. And so the name zero divisor means exactly what you think it does. You found something non-zero that divides it. Okay. So what's important about zero divisors is often we don't like zero divisors. And so we're going to focus at times on a special type of ring, which is called an integral domain. And what an integral domain is it's a type of nice ring. And it's nice because it's a commutative ring with unity. So multiplication is commutative, and it has a multiplicative identity. And there are no zero divisors. So anytime that we multiply 2 non-zero elements of the ring together, we know that we are not going to get 0. And so this is, in some sense, integral domains is we often don't like to get 0. We like that if the important idea with integral, if we're in an integral domain, and so if R is an integral domain and we have A and B are inside of R with A times B equal to 0, then in an integral domain, this can only happen if and only if A is equal to 0 and or B is equal to 0. And so this is, if you think about, solving things with, say, polynomials, this is an important property to have. If you factor a polynomial and you set it equal to 0, it's important to know that that means that at least one of the parts is equal to 0. So, as we said, examples of integral domains: integers, rational numbers, real numbers, complex numbers are also integral domains. Z mod nz is not going to be an integral domain if n is composite, right? And so if n is composite, i.e., there exists A times B that equal n, with both of them strictly bigger than 1 and smaller than n, well, then that means that you can think about these as being inside Z mod nz. They are not equal to 0, but A times B is going to be congruent to 0 mod n. And so that means that they are zero divisors, and that means that Z mod nz cannot be a integral domain. If n is prime, if we're dealing this with a prime, then the only way that we can factor two things, anytime we have a product of two numbers that are multiply up to a multiple of the prime, is that if one of the two numbers was already a multiple of the prime. And so that means that in the ring, Z mod nz would already be 0. And so you can't have zero divisors in a Z mod nz if the modulus is prime. If R is an integral domain, then polynomials and formal power series will both be integral domains as well. And for polynomials, we will give a proof of that in a couple videos down the line. But this is an important fact. And so this allows us to do things such as factoring with polynomials. Okay, so now, important thing with integral domains is that not only can we do cancellation with addition, but we can also do cancellation with multiplication. So in an integral domain, if we have A, B, and C are elements of it, and we know that A is not equal to 0, then if we have A times B is equal to A times C, then it must be that B equals C. And the idea is, if A times B equals A times C, then A times B minus A times C is equal to 0. And then we can use the distributive property and the basic properties of rings that we saw before, and we can factor the A out and get that this means that A times B minus C is equal to 0. And so we have the product of two things equal to 0. And if A is non-zero, the only possibility then is that B minus C is equal to 0, which then means that B is equal to C. Okay, and so this is the proof of this. And so we can do left cancellation if we are in an integral domain. If we're not in an integral domain, that means that we cannot do that. So if you think about matrices in general, matrices are not integral domains. And so you can't do left cancellation in using matrices because it is not an integral domain. So a field is a commutative ring where every non-zero element has a multiplicative inverse, so is a unit. And so basically what happens is that if F is a field, if and only if, when you take 0 away, you have a abelian multiplicative group. And so not only is it a multiplicative group, it really is abelian. Okay. And so rational numbers, real numbers, complex numbers, these are all examples of fields. You know, if you take anything that's non-zero in them, you take any R that's in any one of these, and you know that R is not equal to 0, then you can talk about 1 over R. And so since R times 1 over R is going to equal 1, this says that R is a unit. And so since this is true for everything that's non-zero, that means that these sets are all fields. So rational numbers, real numbers, complex numbers, these are rings that are integral domains that are fields. Z is not a field, right? There is nothing times 2 there's no integer times 2 that gives you back 1, right? The solution to this would be n equals 1/2, so that doesn't happen. So in fact, in the integers, the only units in the integers are 1 and minus 1. In general, if you start with a field and then you look at the polynomials over the field, so the polynomials with real coefficients or polynomials with rational coefficients, that is not going to be a field. Similar to the set of formal power series, that is also not going to be a field. And that's just because generally the x itself, which is going to be an element of that, is not going to be a f itself. X itself is not going to have an inverse, and so that prevents it from being a field. However, if you, instead of adjoining a variable x, you adjoin something which is algebraic, which is the solution to a polynomial, then that is going to give you a field, right? And so if we think about this q adjoin I, so this is the integers plus anything that is I times an integer. And so that's what we mean by this. Or really this technically means this is anything that can be written as q times a polynomial in I, but it turns out in this case with I, and this is something that's interesting to think about, that if you think about any polynomial with I plugged in, you can always write that as a plus ib in some way. Same thing with square root of n. This actually is a homework problem that you were that you can do if you would like. So big theorem, and so this is, we're going to be closing up on this video pretty soon, and so this is sort of the one big theorem to finish this up on, is that if you have a finite integral domain, so remember an integral domain, that means that there are no zero divisors, then a finite integral domain has to be a field. Okay, and so what's the proof of this? So let's let R be an integral domain. Then we have that, let's let A be an element of R with A not being 0. And so hopefully this theorem, this proof is going to look familiar. We're going to look at A squared, A cubed, all the way down, all the powers of A, just A multiplied to itself. Since this is a ring, this is allowed. Multiplication is closed, and so these are all elements inside the ring. Since R is finite, by the pigeonhole principle, we have an infinite list inside a finite set, so things have to start equaling each other. There exists some I and j with a to the I equals a to the j. Now, since we are inside an integral domain, let's say I is less than j, then I can cancel off the ai on the left, and we have ai is equal to ai times a j minus I, and so canceling off, which we're allowed to do because we're in an integral domain, we get that 1 is equal to a times j minus I, whatever that is. And so in particular now we can factor 1a out, and we have a to the j minus I minus 1. That is equal to A inverse. Okay, and so this means that we've shown that for any non-zero element in the integral domain, we have found that it is a unit, it has a multiplicative inverse, and so since this is true for everything that's non-zero, that's what it means to be a field. Okay, so finite integral domains are all fields. Now, one finite integral domain that we talked about a little bit before is Z mod PZ, if P is a prime, and so it's finite, it is an integral domain, there are no zero divisors, and so the theorem says that it has to be a field. Last notion that applies to fields is that every field has what's called a characteristic. And so it doesn't have to just be in fields, it can apply to rings in general. So let's talk about what a characteristic is. So a characteristic of a ring is the least positive integer n, if it exists, such that doing n times x, and so literally we mean adding x to itself together n times, gives you 0. Now, if no such n exists, then we are going to say that the characteristic of the ring is 0. Okay, and so some examples of characteristic 0 rings. This would be integers, real numbers, rationals, complex numbers, polynomials over any of these. So the integers, polynomials over the integers, or the rational numbers, etc. Those are all examples of characteristic 0 rings. Z mod NZ, on the other hand, this has characteristic n. If you take anything in there, add it to itself n times, you're going to end up with 0, with the 0 element. Okay, final theorem. Let's start with a ring with unity. So we're going to let R be a ring with unity. If one has, so we know that it has unity 1 in it. If 1 has infinite order under addition, then the characteristic of the ring is 0. On the other hand, if 1 has order n under addition, then n is the characteristic of R. And so really what this is saying is that the characteristic of a ring, this is equals the additive order of 1 if the additive order of 1 is finite. Okay. And so if 1 has infinite order, then there's no n such that you add 1 together n times and get 0, and so characteristic there is 0. So 1, you found an element such that it doesn't work, and so that right there gives you that the characteristic is 0. So there's nothing left to prove there. On the other hand, let's say that 1 has order n. Well, then if we take any other x in the ring, look at x plus x plus x n times, well, applying the distribution rule over and over again, we can rewrite this as 1 plus 1 plus 1 plus 1 n times x. But then all those 1's added together n times. Well, 1 is its order under addition. And so we get 0 times x, which is 0. So x added to itself n times gives you 0. And so this, since this is true for everything in the ring, then this means that the characteristic of the ring is n. So, using important corollary of this is that the characteristic of an integral domain has to be 0. If it's not 0, then it's going to be prime. So let's give a quick proof of this. We're going to suppose that the characteristic is non-zero. So suppose characteristic of integral domain R is not 0. So we're going to prove that it is prime. And so let's let characteristic of R equal n. And let's suppose we have some positive integers L and K such that L times K equals n. So these L and K, these are both greater than 0. Okay. Well, then I can look at adding 1 to itself together L times 1 to itself K times. And so really I have L1s plus K times K1s, L1s times K1s. And if you did this out, you end up with L times K, total 1s, but we said that L times K is n. And so this is 1 added to itself n times, which is equal to 0. And so the only possibility, if we have two different elements of the ring multiplied together equals 0, since we're in an integral domain, the only possibility is that one of them had to already be 0. So either 1 added to itself L times equals 0 for, so we'll say 1 plus S for L or K, and that would mean that they already were a multiple of, by the previous theorem, this means that they are already equal to n. So equal n. And so this would mean that the only possible way that you could factor n is by having it be n times, in this case, the other factor would have to be 1. And so this means that n is prime. So n is prime. Anytime that, let me say it over again, the idea of this argument over again, if you could take any factorization you want of n, if you think about multiplying together ones that many times, that would mean that one of those would have to be equal to 0. So any factorization, you'd have to have one of the factors was already n. And that only happens if something's prime. That is all for this video. I know it's been a long one, but again, I think the ideas here, these should be ideas that that deep down you are familiar with, and this is just really just putting some new names onto them. And I will see you again soon.